Thank you so much. So, good afternoon, everybody. As already said, I'm a PhD student, and today I will present a work that is titled Multi-Omics and Sensory Analysis of Coffea canephora, Assessing the Impact of Roasting Speed on Safety and Energy Efficiency. So basically, this work was born from an observation of the market, in particular the Italian market. We saw that a claim is used in our Italian market, and it is tostatura lenta. It means slow roasting. And you see that from some sentences that are published on roasters' websites, they tell that this slow roasting is providing a smooth, balanced, unmistakable aroma to the coffee. So we wanted to investigate a little bit. To investigate about roasting speed, first of all, we started from Coffea canephora. Then we evaluated the natural gas consumption. We analyzed acrylamide, and subsequently, we performed sensory analysis. For the chemical part, we analyzed the volatiles and non-volatile compounds. We made statistics on the two datasets separately, but in the end, we combined the two datasets to perform a multi-omics approach. Okay, so we started from 4 commercial grades of Indian Coffea canephora. We have Capi, Parchment, and Cherry. We have 2 screen sizes of Cherry. We roasted these coffees with a 5-kilo drum roaster from Joper, and we recorded all the roasting process parameters with Artisan. We used 3 different roasting speeds, namely fast, medium, and slow, but we were able to reach the same roasting degree that was a medium roasting. Okay, first of all, natural gas consumption data. As you may see, we used both a gas meter and the Artisan energy calculator. Unfortunately, real and calculated consumption are statistically different. I tell unfortunately just because, for example, if a roaster wants to use the data from the energy calculator to upload them on blockchain for carbon offsetting, this may be a problem, but the Artisan developers are really making a lot of efforts to improve this instrument. Mainly problems are given by the roaster model and the gas valve that is used. In our case, on the screen of the roaster, we saw a percentage of the full power, but probably that was not the power of the burner, but the percentage of the gas pressure. So the developers are started a project. They wanted to collect a lot of data based on a standard curve to improve this instrument. So we will see in the future. Okay, then we moved to acrylamide analysis. And fortunately, we have all data that are really below our European threshold. So we were able to perform a sensory analysis. We waited 4 weeks to mimic the time that could pass between coffee roasting and its presence on the market. We tasted in espresso brew. Our panel was composed by 7 experts, including 4 Arabica Q graders, and we evaluated the sensory attributes that you see in the slide. Okay, for the chemical part, we analyzed both non-volatiles and volatiles. We used a ultra-high performance liquid chromatography coupled with high-resolution mass spectrometry based on quadrupole and Orbitrap. For the volatile part, we used 2-dimensional gas chromatography coupled with a time-of-flight mass spectrometer. After extraction, acquisition of data, normalization, we used 2 different databases to identify the compounds. In the case of non-volatile, food database. In the case of volatile compounds, the NIST database. Okay, we were able to annotate 1,500 compounds, metabolites for the non-volatile fraction, and 1,248 metabolites for the volatile fraction. We directly moved to a supervised chemometrics using the AMOPLS analysis that basically it's an OPLS-DA analysis but ANOVA mediated. And with this analysis, we were able to assess the effect of each of these factors, so our coffee grade, our roasting speed, but also the interaction between these two factors. These are the results. So basically, from the tables, you see that for both non-volatiles and volatiles, we have some statistical parameters. First of all, the residual sum of square that is giving us an idea of how much a certain factor is contributing to the model. Then we have the residual structure ratio, p-value, that is giving us the information about the ratio between the structure of the data of the factor and the structure of the data of the residuals. And this is what indicates us the statistical significance of this model. You see that, fortunately, they are almost all statistically significant, apart from the interaction between the commercial grade and the roasting speed for the volatiles. In the pie charts, we see we are analyzing just the effect of roasting speed, and for the non-volatile compounds, we have the chemical classes of the top 50 markers, so that are really separating the fast roasting speed from the other speeds, medium and slow. For the non-volatiles, we see that the main classes are phenols in the form of flavonoids and cinnamic acids, but also lipids and lipid-like molecules and carbohydrates. While on the other side, for the volatile compounds, we have different classes, ketones, aldehydes, and pyrazine, pyridines, and pyrols. Okay, we were very satisfied from these results, so we decided to go further with the analysis, and basically we picked the two data sets from the volatile and non-volatile fractions. We fused the data, and we were able to apply a multi-omics approach with a Diablo supervised analysis. Again, the effect we are evaluating is just the roasting speed. When we obtained the new markers from this multi-omics approach, we also applied the Pearson correlation analysis, Pearson correlation coefficients, with the sensory data. Okay, as you may see, the Diablo model is able, from two PCA that are relative just to each of the two data sets, this model is able to combine them to obtain just one PCA, which on the first two components is able to discriminate between the fast and the slow roasting speeds. We are just focusing on these two extremes. In the table, you see the most discriminant chemical classes for these two extreme speeds. And we have some numbers. This is basically, again, a fold change analysis, the one that was shown in the volcano plot before. So as an association with the colors, we have blue with classes, chemical classes that are more represented in the slow roasting speed, and this red for the chemical classes that are more represented in the fast speed. And also negatively, the means are negative for the slow, while they are positive for the fast markers. Okay, at this point we had all these markers, so we decided to look at the literature to find some possible connection with the aroma and flavor attributes of these markers. Again, the colors are indicating the fast or the slow roasting speed. Here you may see some compounds that are classified in the chemical classes you see in the table. Here we have many compounds with sulfur inside, providing mainly a roasted, burnt, but an aroma that is linked to meat, sulfurous aroma. Then here it's interesting to see that carboxylic acids are providing a fruity flavor attribute to the coffee, while we will see that this same role for the fast roasted coffee is provided by aldehydes. In the next slide. Sorry, okay. Here we have phenols, furans, and furanones. In this case, from the literature, we already know that phenols are more abundant in Robusta coffee than in Arabica, but in this case, they are providing a smoky aroma and also a woody attributes. While, on the other hand, furans are giving a coffee-like aroma and flavor to our coffees, and furanones are also providing a sweet caramellic flavor. Okay, in this case, we see aldehydes and pyridines. Basically, it's clear from the roasted burnt attributes that basically aldehydes are contributing to this aroma and flavor in the fast roasted coffees, while pyridines are contributed to the same aroma but in the slow roasted coffee. And again, aldehydes, as I said just 2 slides before, are providing also a green vegetative and floral aroma to these coffees. Okay, you know that moving from chemistry to sensory analysis is always tricky, and in this case, the sensory analysis demonstrated that the only statistically significant variation attributable to the roasting speed is an increase of smoky burnt flavor in the slow roasted coffee. And this is also confirmed by this other parameter. Here in the Pearson's correlation, we see that 20.3% of the slow roasting markers are positively correlated to a smoky burnt flavor. So it's a confirmation of our previous result from sensory analysis. But always from this correlation, you also see that the fast roasting has many markers that are negatively correlated with a smoky burnt rubbery aroma, but positively correlated with a sweet, acidic taste, while bitter seems not to be touched by the different roasting speed. So basically, coming to conclusions, first of all, we decided to investigate the effect of roasting speed. That is something that is not really studied in the literature. Of course, Professor Sara has one paper on this, but I mean, it's something that is not really deepened so much. We focused on canephora, and of course, we had to integrate this work also with the effect of commercial grades and post-harvest processing. The fast roast has the lowest impact in terms of natural gas consumption, but with a fast roast we are able to reach the same medium roasting degree, and also acrylamide was absolutely compliant. And multi-omics is a new approach that was successful in this case. And in particular, it is important to combine the 2 data sets from volatiles and non-volatiles because most markers from the fast roasting are coming from liquid chromatography, while most markers from slow roasting are coming to the gas chromatography. Okay, slow roasted coffee, as already said, has a higher smoky and burnt aroma and flavor, probably given by phenols and pyridines, as confirmed by chemical analysis. And at the end, what we wanted to point out is that, of course, roasters should choose the best roasting profile based on their desired final cup quality, given both by sensory analysis and chemical fingerprinting, but they must look to process contaminant development and also to environmental sustainability. So if the faster speed is less impactful, why don't consider also this aspect? So we need a more holistic approach and integration also of sustainability inside our day-to-day work. Okay, so thank you. I leave here also contact of my colleague. he's the real chemist of the situation, so I really thank him and you for the attention.